Okay, now we will discuss different ways to describe datasets using numerical methods or methods that involve some computations. But before we discuss any of those numerical methods, let me just first make a distinction between a population parameter and a sample statistic. A population parameter is any number that is calculated from all the population measurements that describe some aspect of the population. So if you are describing the minimum, the maximum, the average, or any other computation, as long as it was based on the entire population of measurements, then we call that a population parameter. While a sample statistic is a number calculated using the sample measurements that describe some aspect of the sample. So if your dataset is only from a sample, whatever computation you can get from that dataset, we call that a sample statistic. And it's important for us to know the difference between the two because there are slight differences in the formulas for certain computations depending on the source of data. If it's from a population or from a sample, the formulas will be different. So as discussed before about inferential statistics, the bigger set is the population and the sample is a part of the bigger population. Now, any computation from the population is called a parameter and any computation from a sample is called a statistic. And inferential statistics will help us infer the parameter or make descriptions for the entire population even if your data is only a statistic, even if the data is only from a sample, assuming that the sample is representative. Now, the first set of measures are called measures of central tendency. So here we have different computations that describe the central tendency of a dataset. Now, there are many possible interpretations to the center. A center can be the literal center of the dataset when arranged in increasing or descending order, or it can refer to the average, or it can also refer to the typical value, the most typical value in the dataset. And for each of those definitions, we have a specific measure. We have the first one called the mean, we have the median, and we have the mode. For the mean, this refers to the simple average of the dataset. So the population mean is computed using this formula. The representation for the population mean is the Greek letter mu. And this is computed by getting the sum of all the values in the population and dividing the sum by capital N, or the total number of measurements in the population. While the sample mean is represented by small letter x with a bar on its top, and this is normally read as x bar. The computation is very similar to the population mean. It's just the sum of all the values in the sample divided by the sample size small letter n. So again, it's just a summation of all the values divided by the total, which makes the mean just the simple average. So in this example, if you have a sample of 5 measurements, so the 5 numbers here are all from a sample, the computation of the mean requires the use of the sample mean formula. Because again, the data is only from a sample. So the formula requires getting the sum of all the values and dividing that by the total. So computing for that, you get a sum of 156.3 and the total number of measurements in the sample is 5, giving us a sample mean of 31.26. So the sample mean or the mean is just the simple average of the dataset. The median, on the other hand, is another measure of central tendency wherein the median refers to the value such that 50% of all measurements lie above or below it. So this is literally the center of the dataset. You have an equal number of measurements lower than the median and bigger than the median. And to determine the median, we have to look at the number of measurements. If you have an odd number of measurements, then there will be clearly one number at the center, so just find that, and that will be the median. While if you have an even number of measurements, there will be two numbers at the center, and the median is the average of those two middlemost measurements. So in this example, we have the same data set from the sample. First, we have to arrange the measurements in increasing or descending order to find the median. And now that we have the numbers arranged in ascending order, we just have to find the one at the center. And since there's an odd number of measurements here, we will just have to look for the one at the center, which is 31.65. So the median of this data set is 31. Now, if, for example, there are 6 numbers, so let's say we add another number, which is 33.3, then you'll have another number here that's the biggest in the data set, and now the median will be different. So since you now have 6 numbers, then the median will be the average of the two middlemost. So the median will now be the average of 31.6 and 31.7, or 31.65. And in both situations, in both examples, the median just gives us the number with an equal number of measurements lower and bigger than that value. So in the earlier example, if you have 31.6 as the median, you have two numbers lower than that, and you also have two numbers bigger than that. Or if you had 33.3 as an additional number in the dataset, the median becomes 31.65, then you have an equal number of measurements to its left and to its right, which is 3. So the median is again just the number at the center. Another measure of central tendency is the mode, and the mode is simply the most frequent number in the dataset. So this is the number with the highest frequency. This is the most typical number in the dataset. Now, sometimes in some datasets, 2 or more values have the highest frequencies. So in those cases, we have specific terms for the dataset. So if there are 2 modes, meaning the two most frequent the most frequent number, the highest frequency is from 2 different numbers, so there are 2 modes, and we call the data bimodal. And if there are more than 2 modes, then we can call the dataset multimodal. Or if your dataset is in the form of a frequency distribution where you have intervals with lower and upper limits, then the mode is simply the class or the interval with the highest frequency. Now, we can also interpret or find the mode in different graphs. So from our previous examples, we can find the mode by looking at the histogram. So the bar, which is the tallest out of all the bars in the histogram, is your modal class. Or in a dot plot, the mode is the value in the x-axis that has the most number of dots on top of it. Or in a stem and leaf display, the mode is the value that has the most number of similar consecutive numbers in the same stem. So again, the mode is simply the most typical or the most frequent number in the dataset. Now, another computation that describes the central tendency of the dataset is called the weighted mean. And the weighted mean is very similar to the simple average. However, here we put weights to certain measurements because we use this in cases wherein certain measurements have more impact to the computation of the average. So the weights can be used to describe the importance or the effect of a certain measurement to the computation of the average as compared to the other measurements in the dataset. And to compute for the weighted mean, we have this formula. So you have the summation of W sub I times X sub I divided by the summation of W sub I, where W sub I refers to the weight assigned to the class and X sub I is the value of the class. So here, again, if you look closely at the formula, it asks for the sum of the products. So you have to multiply the weight and the value of X first before you get the sum. In this example, we have a family business that decided to put up a new manufacturing facility with an expected capital outlay of 100 million pesos. And the 100 million pesos can be financed through the following sources. So the 100 million can come from bonds, can also come from preferred stocks or retained earnings or new common stock. Now the 100 million is divided into those four sources. And we can see here the allocation. So 40 million of the 100 million will come from bonds, 10 from preferred stocks, and so on. Now for each of the sources, we have its own cost. So it costs 10% to source from bonds. The interest rate is 11.9% for preferred stocks, and so on. So given that you have different sources of funds and different sources of funds have different costs, how do we compute for the average cost of financing the expansion? So since here the weights are different, the sources have different contributions to the average, it's better to use the weighted mean compared to the simple mean. So again, here we have the four sources. We have their costs and then their amounts. To compute for the weighted mean, again, we need to get the product of W and X. So get the product for each of the rows, and then later we will get the sum. So for the first row for bonds, that's 10% times 40 or 4. Next, 11.9% times 10 will give it will give us 1.19. Doing that for the two other rows, you will get 3 and 4.875. And computing for the sum of all these four values, we have 13.065. So that's the sum of all the values in the data set, all the values of W sub I times X sub I. And to compute for the weighted mean, we have to divide that by the sum of the weights. Now, in this data set, we have two columns. We have cost and amount. How do we determine which of the two columns correspond to the weights? Now, remember, we are computing for the average cost. So, the column for the cost refers to the values of X, since we are getting the average of cost. Now, the weights will now be the amounts. And again, it's incorrect for us to consider the amount as the values of X, because we are not computing for the average amount, but we are computing for the average cost. So it's more appropriate for us to consider the costs as the values of X and the amounts as the values of W. So dividing 13.065 by the sum of the weights, which is 100, we will get 0.136065 or 13.065%. And this is actually called the weighted average cost of capital that you might be discussing in your future finance courses. Now, for the four scales of measurements, there are appropriate measures in describing the center. So for nominal, wherein the variable is divided into different categories where the rankings are not present, the best measure of the middle is the mode. So since there's no ranking, then the best way to describe the center is through the mode, by identifying the most frequent category. For ordinal scale, the best measure of the middle is the median. Remember, for ordinal, there is an order for the categories, so we can identify the one at the center. Now, for interval and for ratios, since both are quantitative, we can use either the mean or the median depending on the shape of the dataset. If the dataset is symmetrical, the best measure of the center is the mean, the simple average. However, if the dataset is skewed, it's better to use the median. Now, why is it better to use the median for cases where the dataset is skewed? Because we know that if data sets are skewed, it's either you have extremely low values or extremely high values, or most of the numbers occur in the lower values of x, or most of the values occur in the bigger values of x. So as shown here in this computation, this is the same example earlier. When we computed for the median, we got 31.6. Now, let's say we replace the lowest number with an even lower number and replace the biggest number in the dataset with an even bigger number. Now, if you do that, the dataset now changes to this. If you are asked to compute for the median, then the median will not be affected because the median only looks for the one at the center. It doesn't really look at the values of all the numbers in the dataset, but it only looks for the one at the center, which makes the median unaffected by extreme values. Therefore, it's better to use instead of the mean for skewed datasets, because we know that when the dataset is skewed and you compute for the mean, the presence of extremely low or extremely large values will significantly affect the computation of the average. Now, aside from describing the central tendency of the dataset, we also have some measures that describe the variation of the dataset. Here in this example, we have two graphs. We have a graph showing us the distribution of repair time in days for American Service Center and the distribution of repair time in days from the National Service Center. Now, graphically, we can see that the two data sets are different, but if the graphs are not present, it might be difficult for us to make a distinction between the two. So first, if you look closely at the graph, the first graph is trying to tell us that 5 items were repaired in 3 days, while 10 items were repaired in 4 days, and 5 items were repaired in 5 days. Now, you can make a similar interpretation for the National Service Center. And if you try to present this using the raw data, then we will have these two data sets. So again, you can see here the difference in terms of the actual values of the numbers. Now, if you only compute for the measure of central tendency, which is the mean or the average, you will get the same mean. They have the same sum, they have the same average of 4. So if you are not presented the graph, it will seem like the two data sets are similar because they have the same mean. Now, if you don't have the graph and you only have the measure of central tendency, we normally add a measure of variation to help us visualize the difference between the two distributions or between the two data sets. Now, the first and the simplest measure of variation is called the range, and this is simply the largest number in the dataset minus the smallest number. And we actually used the range before in computing for the class length for intervals. So the range for the American Service Center is 5 minus 3 or 2, while the range for the National Service Center is 7 minus 1 or 6. So the range here is 2 and the range here is 6. The range for the National Service Center is bigger compared to the range for the American Service Center, implying that the National Service Center's numbers or measurements are more varied or more scattered, and that's something that we can see visually. Now, aside from the range, we also have the variance, because the range is not really the best description of the variation, because we know that the range is affected by extreme values. Because for the range, you only look for the lowest and the biggest. It doesn't look at the values of all the measurements in between. Now, we have another computation called the variance, and this uses all the numbers in the dataset to compute for the description of the variation. And here we make a distinction between a population variance and a sample variance. So the population variance is the population parameter, while the sample variance is the sample statistic. Now, this is a population parameter, so we represent this using another Greek letter, sigma squared. While sample variance is a statistic, so we just represent this with small letter s squared. So the variance is the average square deviation of the individual measurements from the average. Again, it just differs in terms of the source of the data set. So if the population is used, then the square deviation will be based on the population mean. For the sample variance, the deviations will be computed based on the sample mean. And here are the formulas to compute for the variances. For population variance, that's the summation of the quantity x of I minus mu squared from I equal to 1 up to capital letter N. And we divide that by the total population size, capital letter N. Well, for the sample variance, we use a similar process, but now instead of mu, we replace that with x bar, because remember the data is only from a sample. And furthermore, the denominator will now be small letter n minus 1. Now, why do we have to subtract 1? We divide the sample variance by n minus 1 so that we will underestimate the variance. We know that if we subtract 1 from your denominator, then the denominator decreases and it makes the value of the variance higher. So we are able to do that by subtracting 1. And why do we need to overestimate the variance? Because your data set is only from a sample. So it's more conservative, or it's better for us to describe a bigger variance to the data set, especially if your data set is incomplete, if it's only from a sample. Now, another interpretation why n minus 1 is used is through a computation. So it's actually based on the principle of unbiasedness. So the denominator n minus 1 is the formula that will make s squared an unbiased estimate of the population variance. Now, that concept of unbiased estimates will be discussed further in chapter 7. So for now, we will use n minus 1 as the denominator for the sample variance. Now, once you have the population variance, we can also compute for another measure of variation called the standard deviation. So the population standard deviation, represented by sigma, is just the square root of the population variance. And the sample standard deviation is the square root of the sample variance. Now, we compute for the standard deviation aside from the variance because the unit of the variance is not really similar to the unit of the data set. Because if you go back to the formula for the variances, we are getting square deviations. So if you use a particular unit here, the value of x has that unit, the average also uses the same unit, but we get the square. So the unit becomes whatever unit squared. And we can't really interpret the value on its own using the variance because the unit is different. So we get the square root to compute for the standard deviation so that we have a measure of variation that is written in terms of the same units as the data set. So it's no longer unit squared, but it uses the same unit as the data set. So again, these are the formulas for the standard deviations. Now, in this example, we have a data set of 5 class sizes. So let's say there are only 5 sections for QMT 12 during the summer. And the class sizes are shown here, 60, 41, 15, 30, and 34. Now, since there are only 5 numbers in the data set, and the dataset is complete with just the 5 numbers. There are only 5 sections, so we can still consider this as population data. Even if the value in itself is very small, it already represents the entire dataset, so this is still considered as population data. Now, to compute for the variance, you need to compute for the mean first. So to compute for the mean, just get the sum and divide by the total, and we will get 36. And since the dataset is from a population, then we will use the formula for the population variance, which is sigma squared. So that's, again, the average square deviation of each individual measurement to the population mean. So for the first number, 60, you will subtract the average, 36, and then we will get the square of the difference. And then we will do that for the rest of the numbers. 41 minus 36, and again, get the square. So do that up to the last number, and then get the sum, divide that by the total number of measurements, and we will get 216.4. So the unit here will now be students squared. Now, to compute for the standard deviation, again, we just have to get the square root of the variance. So getting the square root of 216.4, we will get 14.7105, and the unit will now be similar to the unit of the dataset. So the unit here will now be students. So it's easier now to interpret the variation of the dataset because the measure of variation is now in terms of the same unit as the dataset. Now, in the car mileage case example, the dataset again comes from a sample, so the formulas will be slightly different. Now, to compute for the variance in the standard deviation, we need to compute for the mean first. So again, the sample contains 5 measurements, so the sample mean is 31.26. And computing for the sample variance in standard deviation using the correct formulas, we will get the following. So again, it's essentially the same process. That's 30.8 minus 31.26 squared plus 31.7 minus 31.26 squared. And do that for all the numbers, but divide that by n minus 1. So that should be 5 minus 1 or 4, giving us a variance of 0.643 and a sample standard deviation of 0.8019. So the standard deviation now has the same unit as the unit of the dataset. Now, if the dataset is too large, unlike these examples where you only have 5 measurements, then you can use other ways to compute for the variances and the standard deviations. Most scientific calculators have statistical functions, so you can compute for the variance and the standard dev quickly using the calculators, or you can also compute for those using Microsoft Excel. There are built-in functions in Microsoft Excel that can compute for the average or the means. You can also compute for the population or the sample variance and standard deviation. So just explore those functions in the calculators and Excel for you to compute for these computations faster. Now, in this example, we have the daily domestic box office in dollars of an international movie for the first 10 days it was screened. Now, for the first question, we need to compute for the mean and standard deviation of the daily box office for its first 10 days of screening. While for the second question, we have to compute for the mean and the standard dev of the daily box office for all the days it was screened. So for the first question, it's asking for the mean and the standard deviation for the first 10 days. Now, to determine the formula that we have to use, just ask yourself if you have all the necessary information to allow you to compute for the mean and standard dev of the first 10 days. Now, we have the information from the first 10 days here, meaning we have the complete dataset for this question. Therefore, to compute for the mean and the standard dev, we have to use the formulas for the population mean and the population standard deviation. Again, we will use population parameter formulas here in this question because it's asking for the first 10 days and data from the first 10 days are available. But for the second question, it's asking for the mean and standard dev for all the days it was screened. Now, do we have data for all the days it was screened? No, we only have the first 10 days. So since the data is incomplete, since the data is only from a sample, then it's better for us to use sample statistic formulas. So compute only for the sample mean and the sample standard def. Now, if you compute for this manually or through your calculators or through Microsoft Excel, the population mean for the first question should be 2,385,429.3, while the population standard def is $1,473,617.273. For the second question, the sample mean should be 2,385,429.3, while the sample standard dev will be $1,553,328.994. So again, the formulas used for these two questions are different because we were being asked to describe two different data sets. For the first one, only for the first 10 days, but for the second one, for all the days it was screened. Now, another measure of variation is called the coefficient of variation, or the commonly just called CV. The coefficient of variation is a combination of a measure of variation and a measure of central tendency. So it uses the standard deviation of the dataset and the mean of the dataset to compute for the CV. So that's just the standard def of the dataset divided by the mean, and you can convert that to a percentage by multiplying that to 100 and adding the percent sign, or you can just leave it as a decimal number. Again, it's just the standard dev over the mean. So it shows us the variation of the dataset in terms of the two measures. So it shows us the relative size of the standard deviation in terms of the mean of the dataset. So in this example, we are interested to compare the travel time when taking two different routes from your house in Quezon City to your office in Makati. The following travel times were recorded. So for EDSA, you have 5. For C5, you also have 5. So we need to compute for the mean, variance, standard dev, and CV of all the travel times. First, you have to identify if the dataset is from a population or from a sample. We were asked to compute for computations describing the travel times using each route. Now, do we have data for all the possible travel times using EDSA and using C5? No, you only have 5 for both. So we can consider these two as sample datasets. As such, we have to use formulas for sample statistics. So if we compute for those values using the formulas or the calculators or your Microsoft Excel, you should get the following values. So the mean for EDSA is 157.4, while the mean for C5 is 153.8. Sorry, the unit here should not be dollars, it should be minutes. So for variance, it should be minutes squared, and for the standard deviation, it should also be in terms of minutes. If you try to interpret the values here, we can interpret in terms of the measure central tendency and measures of variation. If you look at the mean, we can see that the average for EDSA is bigger compared to the average for C5. So we can say that on average, the travel time using EDSA is bigger as compared to C5, or travel times using C5 on average is faster. But if you look at the measures of variation, we can see that the measures of variation for C5 are bigger as compared to the measures of variation in EDSA. In fact, for all the three measures, the measures are all bigger for C5 compared to EDSA. So what is this trying to say? It's simply trying to say that the measures using C5 are more varied, more scattered. So there is a bigger tendency for the measurements here to be more erratic. So it's not as consistent as EDSA because of the bigger measures of variation. So to conclude, again, although on average, the travel time using C5 is faster, the travel times using C5 are not consistent. So it's either you get there, the travel time is really fast, or the travel time is really big. Now we also have some computations involving group data or involving frequency distributions. So for cases wherein you only have the frequency distribution available, so you don't have the raw data anymore, we can still try to estimate the mean and the variance of the dataset even if you don't have the exact numbers. Now, to compute for the mean and the variances, we have the following formulas. So for the mean, we have the summation of the frequency multiplied to the midpoint of the class divided by the total number of measurements in the dataset. So it's the similar pattern for both the population mean and the sample mean. So in the apartment rents example, we have a sample of monthly rent values for one-bedroom apartments. So it's only from a sample of 70 apartments, so we can only compute for sample statistic. So we will use the formula for sample mean. So again, if you don't have this data set, for example, you only have this data set, you only have the intervals and the frequencies, then we can still try to estimate the mean using this approach. So we don't know, let's say again, you only have this data set. We don't know the exact values of all those 25 numbers, but we just know that there are 25 numbers between 425 and 453. So to try to estimate the average, we will need to compute first for the midpoints of the classes. So again, the midpoints are just the average of the lower and the upper limits. So the midpoints for all these classes are shown here. And to compute for the mean, again, we have to multiply the midpoints to the frequencies. So for the first row, that's 25 times 439 or 10,975. Do that for all the classes and then get the sum. You will get 34,286. Now divide that by the total number of measurements. We will have an estimated sample mean of 489.8. Now this is only an approximation because remember, you don't have all the exact numbers in the dataset. Now if you used all the 70 numbers to compute for the mean, the actual average from the sample is 490.8. So as we can see here, even if you only use the approximation formula, they only differ by 1. So this is still a good approximation of the average even if you don't have or even if you don't use all the exact numbers in the dataset. Now we can also compute for variances of group data, and here are the formulas. So for the population variance, that's the frequency times the square deviation of the midpoints of the classes from the population mean, and then divide the sum of this computation by capital N. Whereas for the sample variance, instead of mu, this is x bar, and instead of n, this becomes n minus 1. So for the same data set, which is from a sample, we will use the formula for the sample variance. So we need to compute for this quantity. So for the first row, that's 25 times 439 minus the mean, which is 489.8 squared. So if you compute for that, you will get 64,516. Now do that formula or do that computation for all the other rows and you'll get the following values. And then getting the sum will give you 218,411.2. Now to compute for the sample variance, again, we divide this value by small letter n minus 1. So divide this by 70 minus 1 or 69 and you will get this sample variance, 3,165.3797. And it will give you a sample standard deviation of 56.2617. Now again, this is only an approximation because you only used the midpoints. You only used the group data. Now if all those numbers are available and you used all those individual numbers to compute for the standard dev, the actual standard dev is 54.7372. And again, it's not equal to the one we got earlier. However, it's still relatively close. It's still very close to the actual number, which is 1.5245 units away only from the actual standard dev. So again, we have these formulas that can help us compute for the mean and the standard def of datasets if you only have group data, if the raw data are no longer available. Now, here is an example. So you can try to compute for this on your own. So only given this frequency distribution, compute for the mean and the variance and the standard deviation of the dataset. Now, aside from the manual computation shown earlier, you can also compute for this faster using your calculators or using Microsoft Excel. So just try to explore again the features of your devices to determine the faster way to compute for these values. Now we have another set of descriptions that try to describe the shape of datasets through computations. First is called skewness. So the skewness again refers to the shape of the dataset. So we can have a skew to the right or skew to the left or a symmetric distribution, and it tells us where most of the data is concentrated. Now, we can describe the skewness of the dataset through a computation, and one possible way to describe skewness is through Pearson's median skewness coefficient. And the computation is shown here. The formula is 3 minus mean minus median over the standard deviation. And the value of the Pearson's median skewness coefficient will tell us the skewness of the dataset, even if you don't have the graph. So, if you compute for the coefficient and the formula gives you a 0 skewness coefficient, it says that the distribution is actually symmetrical. And if you go back to the formula, when will you get a skewness coefficient of 0? It will only be possible if the mean and the median are equal. That's the only time when the skewness coefficient will be equal to 0. So if the mean and the median are equal to 0, it suggests that the distribution of the dataset is symmetrical. And here is an example. It's a normal distribution that's bell-shaped and symmetrical. Now, if you compute for the skewness coefficient and you get something that's positive, then it says that the distribution is skewed to the right. So, again, looking at the formula, the skewness coefficient will only be positive if the mean is bigger than the median. So that is actually shown here. This is skewed to the right tail is longer than the left tail. The mean is bigger than the median, that's why the skewness coefficient is positive. Now, first, why is the mean bigger than the median? Because we know that in skewed to the right distributions, you have extremely large values. The median is not affected by extremely large values, unlike the mean. So if you have extremely large values, we know that the mean gets pulled up. That's why the mean is bigger than the median for skewed to the right distributions. If the skewness coefficient is instead negative, it suggests that the dataset is skewed to the left or left skewed. And again, the formula will only give you a negative skewness coefficient if the mean is lower than the median. And again, the mean is lower than the median for left skew distributions because of extremely low values. So the median is unaffected and the mean is pulled down by the extremely low values, which makes the skewness coefficient negative, or which makes the distribution skewed to the left. So here is a summary of the three. So again, the skewness coefficient can help us describe the skewness or the shape of the data set without looking at the graph. Now, the absolute value can also give us more information about the skewness. So the bigger the absolute value, then the more skewed the data set looks like. So for the apartment rents example, earlier we determined that the average of all these numbers is 490.8. So if we are to try to describe the shape of this data set using the skewness coefficient, we just need to look for the median. There are 70 numbers, so the median is the average of the two middlemost, and the two middlemost numbers are 475 and 475. Now the median is 475 compared to the mean. The median is lower, so this is trying to say that the distribution is skewed to the right because the mean is bigger than the median. The mean here is 490.8. Now, aside from skewness, we can also describe the shape of the dataset using the concept of kurtosis. So, kurtosis is another measure, and this measures the sharpness of the peak and the thickness of the tails of a distribution. And this is one way to describe, one way to compute for the kurtosis. That's the summation of x sub I minus the sample mean, or the mean of the data set, from I equal to 1 up to small letter n, and then divide that by the total number of measurements, and divide that by the standard deviation of the data set raised to 4. So the kurtosis helps us describe the sharpness of the peak and the thickness of the tails of your data set. Here we have three data sets, and the kurtosis of the three data sets are also shown below. So the red curve is the curve of the normal distribution where the kurtosis is equal to 3. The blue curve, on the other hand, has a kurtosis of 4. So the kurtosis is bigger than the normal distribution, and we now call this leptokurtic. So leptokurtic distributions have sharper peaks and thicker tails as compared to those with lower kurtosis. While the green curve is a curve with kurtosis of 2.7, so it's lower than the kurtosis of the normal distribution, and we call that platykurtic. So as compared to the first two distributions, the peak is not as sharp, so it's flatter, it's broader, and in terms of the tails, they're thinner because the graph is also broader, so it's wider, making the tails thinner. So the kurtosis is again one other way for us to describe the shape of the data set. Now we have another set of computations that try to describe the position of measurements compared to other measurements in the data set. One such computation is called the z-score. A z-score shows us the distance of a certain measurement from the mean of the dataset in terms of the standard deviation. So this is computed, the z-score is computed using this formula. That's the value of the variable minus the mean of all the values in the dataset divided by the standard dev of all the values in the dataset. So the z-score again just shows us the distance of the value of the variable from the mean in terms of standard deviations. And z-scores can be positive or negative. So if the z-score is positive, as shown here in the formula, it means that the value of the variable is bigger than the average. while if the z-score is negative, it indicates that the value of the variable is lower than the mean of the dataset. So again, here is an example of a dataset which is bell-shaped and symmetrical. So that is x. Now, all values of x can be converted to z. So when you convert x to z, the average of the dataset becomes 0, and then one standard deviation to the right of the mean is equal to a z-score of 1. So again, a z-score is a way for us to determine how far a certain number is from the average. And the bigger the absolute value of the z-score, the bigger the distance of the measurement from the mean. Now, also, again, the sign dictates where the measurement is located. So if you have -3 and +2, -3 is obviously to the left of the average, so the measurement is lower than the average, while if the z-score is +2, it means that the value of the measurement is bigger than the average of the dataset. And if you compare -3 and +2, we can determine which of the two is closer to the mean. And between the two, the closer is 2 because it has a lower absolute value, which is 2. Now, another concept that is used commonly to describe position of measurements compared to the rest of the numbers in the dataset is through percentiles. Aside from percentiles, we also have quartiles and we also have deciles. So in a set of measurements arranged in increasing order, the pth percentile is a value such that p% of the measurements fall at or below the value, and 100 minus p% of the measurements fall at or above the value. So, for example, if you compute for the 10th percentile, the 10th percentile is the number such that 10% of all the numbers in the dataset are lower than that value, and 90% of all the numbers in the dataset are bigger than that value. So the 10th percentile can also be called the first decile. So the percentile is denoted by capital letter P with the subscript. So the 10th percentile is capital P sub 10, while the first decile is capital D sub 1. Now, another common percentile that's computed is the 25th percentile. So that's P sub 25, or that's also known as the first quartile, or Q sub 1. So the 25th percentile or the first quartile is a number such that 1/4 or 25% of all the numbers in the dataset are lower than that value, while 75% of the numbers in the dataset are bigger than that value. Another commonly computed percentile is the 50th percentile, or also called the second quartile, or the 5th decile, or the median. The 50th percentile is the number where in 50% are lower and 50% are higher, which is, again, technically just the same as the median. The third quartile is Q sub 3. This is also known as the 75th percentile. So this is a number in the dataset such that 75% are lower and 25% are higher. So again, these are just the common ways to compute for commonly computed percentiles and quartiles when trying to describe datasets. Aside from that, we also compute for the interquartile range, or IQR. That's the difference between the third quartile and the first quartile. And this is actually used in a computation later to describe the presence of outliers in datasets. Now, percentiles are commonly used in universities. For Ateneo, for example, we use percentiles in making decisions about the admission of applicants to the university. So for students, the applicants are after checking the results of the entrance test of the applicants, they are summarized, and instead of using the exact scores of the students, the dataset presents the percentiles of the students instead in different areas of the test. For example, if you have the first applicant and you look at the column for math and the value shown there is 95, it means that the score of that student for math is the 95th percentile, meaning the score of that student is higher than 95% of everyone else who took the test, and only 5% are higher than that student in math. So most universities, in particular Ateneo, uses percentiles to make decisions because it's a more fair way of looking for those who will be admitted. Now, percentiles are used because the difficulty of the entrance tests are definitely different every year, or for every batch, the performance of the students are different. So to make sure that the number of admitted students are equal, or that the university will get the best students from all the applicants, then the university uses percentiles instead of a fixed passing score. Because if there is a fixed passing score, let's say of 75, then for some years, maybe many students will pass, but for some school years, there will only be a few students who will pass. So to make sure that students admitted will be relatively the same, Ateneo uses percentiles instead of raw numbers. Now, to compute for percentiles, we have the following steps. First step is to make sure that the measurements are arranged in increasing order. Next is to compute for an index, and an index is equal to p over 100 times n, where p is the percentile that you are looking for and n is the number of measurements in the dataset. Now, the third step is used to identify the value of the actual percentile. The previous step only computes for an index, and the index is used to determine the actual value. Now, if the index is not an integer, we have to round it up to the nearest integer, and the next integer greater than I denotes the pth percentile. While if the I is an integer, then the pth percentile is the average of the measurements in the ith and I plus 1th position. So in this example, we have a data set of 12 numbers that are already arranged in increasing order. So if we have to compute for the 10th percentile, again, we have to compute first for the index. So the 10th percentile is the one being asked here. So P should be 10. And there are 12 numbers in the dataset, so n is equal to 12. So computing for the index, we will get 1.2. And according to the rule earlier, since the index is not an integer, we have to round it up to the nearest integer, which is 2. And 2 is not the percentile, but the position of the percentile. So out of all the numbers in the dataset, the 10th percentile is actually the second number in the dataset, which is 11,070. So 11,070 is the 10th percentile, which means that approximately 10% are lower than this and 90% are bigger than 11,070. For the first quartile, or the 25th percentile, we use the same formula, p over 100 times n. So that's 25 over 100 times 12, or 3. And the rule states that if the index is an integer, we have to get the average of the ith and I plus 1th number in the dataset. So the third number is 18 to 11, and the fourth number is 26,817. So get the average of the two, and we will get 22,514. So that's the 25th percentile, which says that 25%, or 1/4 of the numbers, are lower than 22,540. So if you check that again in the dataset, you have 12 numbers. 1/4 of 12 is 3. And if you look for 22,514, that's in between these two. So there are three numbers lower than 22, 5, 14. Because again, 3 out of 12 is 25%. So that's how we compute for percentiles. So you can do the rest, try to compute for the second, the third, and the 90th percentile on your own. Now we have another example here where you only have a sample of 10 applicants. So the scores are already arranged in increasing order, so you can directly proceed to the computation of the index to determine the percentiles. So if you are asked to determine the minimum score to be part or to be qualified for management honors is an honors program, so you have to be part of the top 15%. So to determine the minimum score to be part of the top 15%, then you have to compute for the 85th percentile. So the 85th percentile, compute for that using the same formula that was shown earlier. Now, in this question, you are asked to determine the approximate percentile of the student who got the score of 89. So it's the opposite. Instead of looking for the percentile, we are asked to determine the approximate percentile of 89. So we want to know if this is the 60th or the 70th or the 90th percentile. So 89 is the 8th number in the dataset. So if you try to count the number of measurements lower than 89, you have 7, which means that there are 7 numbers lower than 89. So you can say that 89 seems to be the 70th percentile. Now, if you look at the numbers bigger than 89, there are 2. That's 93 and 99. So you can interpret 89 as the 80th percentile because 2 out of 10 are bigger than 89. So between 70th percentile and 80th percentile, we will pick the one at the center, which is 75. So 89 is approximately the 75th percentile of the dataset. And you can verify that when you compute for the 75th percentile. So that's 75 over 100 times 10. It will give you an index of 7.5. And according to the rule, you have to round it up to 8. And the number at the 8th position is, again, 89. Now we proceed to computations that describe ranges of datasets. So certain ranges of datasets can be interpreted using different concepts. First, we have the empirical rule for normal populations. The empirical rule for normal populations state that if you have a normally distributed dataset, then the interval, which is one standard deviation to the left and to the right of the mean, is 68.26%, contains 68.26% of all the numbers in the dataset. While if you get the interval 2 standard deviations from the mean, that interval contains 95.44% of all the measurements in the dataset. While if you consider the interval 3 standard deviations from the mean, the interval contains 99.73% of all the measurements in the dataset. If we show that visually, we have here the graphs. The first one shows us the interval 1 standard deviation from the mean, so 1 to the left and 1 to the right. It gives you a proportion of 68.26%. But if the interval is 2 standard deviations from the mean, the percentage is 95.44%. And finally, the interval 3 standard deviations from the mean gives you a proportion of 99.73%. Now, for example, if you look at all the asset takers, and for example, let's say the scores of all the asset takers is normally distributed and you have a total of 10,000 asset takers. Let's say the average of the scores is 60 points and the standard deviation of all the scores is 10 points. Then using the empirical rule, we can make these conclusions. 68.26% of all the scores out of the 10,000 students are between 50 and 70. Because 50 and 70 are 1 standard deviation away from the mean. Or you can say that 68.26% of 10,000 or 6,826 students have scores between 50 and 70. Now, the interval 2 standard deviations from the mean is 40 to 80. So that's 2 times 10 plus added and subtracted to the mean of 60, giving you 40 and 80. So 95.44% of all the scores of asset takers are between 40 and 80, or around 9,544 students have scores between 40 and 80. Finally, the interval 3 standard deviations from the mean is 30 to 90. So 99.73% of all the asset takers, or around 9,973, have scores between 30 and 90. So that's how we interpret the empirical rule. Now, another theorem that we can use to describe the data ranges is through Chebyshev's theorem. Unlike the empirical rule, which only applies to normal distributions, to bell-shaped symmetrical distributions, Chebyshev's theorem can be used for any distribution. So this can be used regardless of the shape of the distribution of your dataset. So here we still have mu and sigma as the mean and the standard def of the dataset. And for any value of z greater than 1, we can estimate the proportion of measurements within that interval using this formula. That's 100 times 1 minus 1 over z squared percent. So this is the approximate percentage of measurements inside that interval. So at least this percentage is the percentage of measurements within this interval. Now again, although this can be used for any dataset which is not normally distributed, this is ideal only for datasets that are single peak. So this should be corrected. This is practical or ideal for single peak datasets that are not very skewed. So datasets that are not normally distributed but are relatively skewed. So it's not very skewed, and at the same time, the dataset only has a single peak. So for example, if you were asked to use Chebyshev's theorem to find the percentage of values that fall between 123 and 179 for a dataset with a mean of 151 and a standard def of 14, we can use the formula shown earlier to answer that question. So again, the interval given to us is 123 to 179. So first, find the z-score, or the number of standard deviations away from the mean of each measurement. So 123, when converted to z, is negative 2, while the z-score for 179 is 2. So in other words, the interval 123 to 179 is just 2 standard deviations away from the mean. So the z for the interval should be 2. So use 2 to compute for the proportion inside the interval. Now, if the dataset was normally distributed, we can say that the proportion is 95.44%. But if you don't know the distribution of the dataset, then it's better to just use Chebyshev's theorem. So again, the value of z is 2. So plug in 2 to this formula. That will be 1 minus 1 over 2 squared, or 1 minus 1 over 4, or 3 over 4 of 100%, or 75%. So according to Chebyshev's theorem, at least 75% of all the numbers in the dataset are between 123 and 179. So we make that conclusion if we don't know the distribution of the dataset. Now, if the dataset was actually normal, does not mean that our interpretation using Chebyshev's theorem was incorrect. Earlier, we concluded that the interval 123 to 179 contains at least 75%. So if the dataset was actually normal, the actual percentage is 95.44%, which shows us that even if you used Chebyshev's theorem, the interpretation made is still correct. We only said that the proportion is at least 75% and the actual value is at least 75%. So that interpretation is still correct. However, again, it's not as accurate as compared to using the empirical rule if the dataset is normal. Now, in the another question is slightly different. Here we are asked to find the interval that contains at least 90% of all the measurements in the same dataset. So now we are not given an interval. We have to look for that interval that contains at least 90%. So the formula 100 times 1 minus 1 over z squared percent gives us 90% according to this formula, to this problem. So we will equate the two in order to answer the problem. So if you equate the two, that's equal to 90%. So divide everything by 100 and remove the percent sign. You will get 0.9 here on the other side and 100 will be removed. So simplifying this, so transfer 0.9 to the other side, transfer 1 over z squared to the other side. You will get 0.1 equal to 1 over z squared. Cross multiply, you'll get 0.1 z squared equal to 1. And then multiply both sides by 10. You'll get a z-score of square root of 10. Now, this will be the z-score that will be used to compute for the interval. So the z-score is square root of 10. So we will get mu minus the square root of 10 times sigma to mu plus the square root of 10 times sigma. So the mean of the dataset is 151. The standard depth of the dataset is 14. Computing for the lower and the upper limits, we will get 106.7281 to 195.2719. So this interval contains at least 90% of all the numbers in the dataset. Now, another way for us to describe the dataset is through a 5-number summary. Actually, this is a visual method or a visual way of describing the dataset. However, we can only discuss this now after we have discussed the concept of percentiles, because the 5-number summary uses the smallest and the largest measurements and the first, the second, and the third quartiles. And the 5-number summary is presented visually using a box and whiskers plot, or according to other references, this is called a box plot. Aside from that, we can also compute for inner and outer fences. These fences are used to determine the presence of outliers in the dataset. So for example, for the inner fence, that's 1.5 times the IQR to the left of the first quartile and to the right of the third quartile. So the IQR, we know that the IQR is just the difference between the third and the first quartile. So that's the same value multiplied to 1.5 to get the inner fences. While for the outer fences, that's 3 times the IQR to the left of the first quartile and to the right of the third quartile. And the existence of values in reference to these fences determines the existence of outliers. So we can tell if measurements are outliers based on these inner and outer fences. If measurements are in between the inner and the outer fences, we can call them mild outliers. But if the measurements go beyond the outer fences, then they are called severe outliers. So in this example, we have a box and whiskers plot wherein the lowest number in the dataset is equal to 7. The biggest number in the dataset is equal to 10. The first quartile of the dataset is equal to 7.5. The second quartile or the median is equal to 8. And the third quartile is equal to 9. So as you can see here, the quartiles form the box. So we put the lines above the point along the x-axis and we form the box based on these 3 quartiles. And to add the whiskers, we have to look at the lowest and the largest values. So the left whisker is from the first quartile to the lowest number, and the right whisker is from the third quartile up to the largest number in the dataset. Now, to compute for inner and outer fences, again, we need to compute for the IQR first. The IQR is just the third quartile minus the first quartile. So that's 9 minus 7.5, which is 1.5. So if you multiply 1.5 times 1.5, we will get 2.25. And that's the distance of the inner fences from the first and the third quartiles. So 2.25 units to the left of the first quartile 7.5 is 5.25. And this is the location of the inner fence. For the other inner fence, that's the same distance to the right of the third quartile. So it's 2.25 units to the right of 9 or 11.25. Now for the outer fences, it's similar. However, we multiply the IQR by 3 instead of 1.5. So again, the IQR is 1.5. So that's 1.5 times 3 or 4.5. 4.5 is the distance of the outer fences from the first and the third quartiles. So if the first quartile is 7.5, we will subtract 4.5 to this for us to get the outer fence, which is 3. While if for the other side, the third quartile is 9, you will add 3 times the IQR or 4.5 to this to get the outer fence, which is 13.5. So that's how we determine the inner and the outer fences. And here are some examples. Some measurements in the dataset fall between the outliers. So between the inner and the outer fences. So we can call them mild outliers. While extreme outliers are those that go beyond the outer fences. And the suggestion is to remove outliers in the dataset to make the dataset more symmetrical. Now, how is it possible to get outliers if these are the whiskers? Remember, these are the lower and the upper limits, or the biggest and the lowest numbers. So how is it possible for measurements to go beyond the fences? In this example, the box and whiskers plot can be constructed based on a preliminary survey. So let's say you conducted an initial survey of 30 respondents, and based on the 30 respondents, you computed for the values here, the 5-number summary, which is shown here. Now, if you continue with the data gathering, it's now possible for us to get numbers that go beyond the lowest and the biggest numbers from the preliminary survey. Also, it's also possible for the whiskers to actually go beyond the fences. So if your lowest number is very, very far from the rest, let's say your lowest number is actually equal to 0.5, that's possible. It will not really affect the value for the first, the second, and the third quartiles, because these values are not affected by extreme values. They're only looking for the percentage within certain intervals. So if the lowest number is actually 0.5, then the whisker will extend to 0.5. So now it's possible for measurements to be outside the fences. So again, box and whiskers plots can be used to determine the presence of outliers in datasets. And that's the end of the part on numerical methods, and that's the end of descriptive statistics.